So I'm going to just quickly do this. Propanol is C3H7OH. Remember, if you don't know what a compound is right now, simply Google it. Because if they're talking about propanol, you can just Google it and figure out what the formula is. It burns and it produces CO2 and H2O. This is what was happening. And the balanced equation was that one molecule is going to produce 3 CO2s and it's going to produce 4 H2Os. And the number of oxygens are going to be, that's 6 plus, that's 10. So there's one already, so there should be 9 over here. So this would be 4.5. Now the question was that you've got 0.1 moles of propanol. They gave you 0.1 moles of propanol. So 0.1 moles of this thing. And they also gave you oxygen as well. You remember, if both quantities are given, then it's a limiting and excess question. So 12 dm cube of oxygen, you can figure out the moles. Moles, and it is under room conditions. TK, just make sure it's at room condition. Only then can you use the 24 dm cube thing. So it's going to be 12 divided by 24. That's going to be 0.5 moles. TK, that one is going to be 0.5. So you've got 0.5 moles, right? Which one is in excess? So it's a limiting and excess reactant questions. One way to figure out which one is in excess is by dividing the moles by their ratio. 0.1 divided by 1, 0.5 divided by 0.45, 4.5, and the number that is bigger in size, that's the one that's in excess, which is 0.5. That's the one that's in excess. Remember, I told you how to spot the one that's in excess. 0.1 divided by 1, this is 0.5 moles. Divide that by its ratio, which is 4.5. So this number comes out to be a bigger value. So this is the one that's in excess. Which means that it is more than the required amount, and this value is not going to take part in the reaction. And TK, is this clear? This thing?
Yes.
TK, Emma, this is clear, Anna? Clear? Now, now the thing is, moving forward, according to the ratio, 0.1 moles will react with 0.45 moles, because that's what the ratio is. It's 1 ratio 4.5. So 0.1 would react with 0.45. So it's clearly in excess. And according to this ratio, 0.3 moles of carbon dioxide are going to be produced. And you're going to have 0.4 moles of water molecules that are going to be produced. So you find the moles, you use the limiting reactant, you find the moles of everything in the equation. Now, what was he asking? He's asking what is the final volume of gas under room conditions. So the first thing is, he's asking for the volume of gas. So you have to focus on the gases. And at room conditions, water is not a gas. So ignore this. He's only talking about gases. So what's the gas that's produced? It's carbon dioxide, right? So how many moles is that? 0.3 moles. How do you find the volume of carbon dioxide gas? That's going to be 0.3. Multiply it by 24 dm cube, and that gives you, what does that give you? 0.3 star 24. So that gives me 7.2 dm cube. So I got 7.2 dm cube. But that is an option, but that's not the answer. The reason that's not the answer is because he's saying what is the final volume of gas. He didn't say what is the final volume of the gases in the products. Because remember, there is some leftover oxygen as well. Not all the oxygen is reacting. So there is some leftover O2 gas. And why is there some leftover O2 gas? Because, just a second. I said, why is there some leftover O2 gas? Because you added 0.5, but only 0.45 are reacting, which means 0.05 moles of O2 gas did not react. Okay, so clearly 0.5 was in excess because only 0.45 took part in the reaction. So you got 0.05 was not taking part in the reaction. And because of that, you can now find the volume of O2 gas that's left behind as well. You can multiply 0.05 by 24. And if you do that, 0.05 multiplied by 24, that gives you 1.2 dm cube. So the total volume of gas that you have is it's 7.2 dm cube of carbon dioxide that's produced plus the 1.2 over here, and the answer would be B. It's going to be 8.4 dm cube. TK, is this clear?
Yes.
Yes, sir.
ठीक है है ना आपने ठीक किया था नहीं the rest अच्छा नहीं I can only see Anna's answer right now. So it's 8.4. So you have to be very careful with gases, especially with leftover oxygen, leftover gases. Okay, a lot of questions they're talking about leftover gases. Even the previous ones that we did, they were talking about leftover gases. Okay, so I think we're done with. You can try these questions at home. Uh, so this is moles and percentage. I'm going to skip that. Or let's do that. Okay, let's do this. This is about empirical formulas, mostly about empirical formulas, but it would involve all types of things. Now, empirical formulas. Empirical formulas are easy to calculate. Calculate. For example, the first question over here. There's n x o y. You don't know n x o y. Let's leave that for now. I'm going to do that after doing an empirical formula question. So let's talk about this one. He's saying in this one, he's saying in leaded petrol, there's an additive composed of lead, carbon, and hydrogen. So there's Pb, and there is carbon, and there is hydrogen, right? Now this is O levels. You have studied this in O levels, how to find empirical formulas. So the percentage mass is given. Sometimes the mass is given. Sometimes the percentage mass is given. Doesn't really matter. It's the same thing. So hydrogen is given as 6.19%. That the formula has 6.19% of hydrogen. It has 29.7% of carbon. So can anyone tell me how much lead does it have? Like all of them together would be 100%. So what you're going to do is you're going to just take 100 and subtract 29.7 from it.
64.11.
Okay, so you're getting 64.11, right? The next thing is empirical formulas always have two steps. One is uh, step number one is you find the moles. Moles would be mass divided by AR. So this is going to be divided by 1, this is going to be divided by 12, and this is going to be divided by whatever lead is. So let me just find out what lead is. Something around 207. You have to be very accurate. Where's lead? Lead is in group 4. So it's 207.2. And we can also confirm the other ones. The other ones are whole numbers. Carbon is 12. This is coming out to be 207.2. Can anyone tell me what the values are? Isaac, can you try and do that? Anna?
So lead ke moles 0.3094.
So you're getting 0.3094 moles. Because we are just working, so use as many decimals as possible. What's carbon 29.7 divided by 12?
2.475.
So you're getting 0.47.
5.
2.4.
That's 2.475. Yeah, are you sure? That's 2.475. So you are getting 2.475, and this is 6.19, obviously. Okay, so that's the first thing. You find moles, just divide by the AR. Now you have the moles of atoms, but that's not a whole number ratio. A formula is usually a whole number ratio. How do you find the whole number ratio? You pick the smallest and divide all of them by the smallest, which in this case is going to be. So the next step is divide by the smallest value. Now I'm assuming everyone knows this. TK empirical formulas are kind of easy to calculate. So you pick, I think 0.3094 is the smallest. So divide everything by 0.3094. What do we get?
Carbon का 7.99
As a 7.99 would be rounded off to 8. TK, you can do that. You can round off things if they're very close to a whole number. Don't round it off if it was 7.5. So what's the last one? 6.19. This is
20.
20.0.
TK, so it's 20. So it's going to be C8 and D would be 20. Now, one thing you should know about this is that there was no need to actually do the lead calculation. I mean, it was just you just if you can figure, because you have to save time somehow. TK, you don't have, there's an extra calculation, there's an extra effort that's going to go into this. Although this is not that much of an effort, you can do this. Nothing wrong with it, but you're always short of time. You have to learn how to save time. So you didn't have to actually do this thing. You could have found the ratio of carbon and hydrogen, and that would have been enough. Like if you I mean, because if you had 8 carbons, you can figure out using the ratio how many hydrogens would you have. Moving on, let's try and do something similar. For example, this one. Now this one you're going to waste a lot of time because the formula has a lot of things. It's I mean, if you do the whole question and you try to find the empirical formula for this compound, then it's going to take a very long time because a lot of calculations would be involved, because you have calcium, aluminium, you've got silicon, you've got oxygen, you've got hydrogen, and the percentages are given. That's 14.04%, and you've got aluminium, which is 14.17%, silicon is 14.75%, and so on. So something H is something, right? They're all quoted over here. Now, if you look at the formula, most of the values are known. The only thing that's not known is, I mean, if you look at the formula carefully, the only thing that's missing is X and Y. So you just have to find X and Y. But you need calcium as well, because you want to find the ratio of aluminium with respect to calcium and silicon with respect to calcium. Like if you had 2 calciums, how many aluminiums would be there and how many silicons would be there? So you don't have to solve for everything. Divide this by 40.1. That's the AR of calcium. Aluminium is, I think, 27, and silicon is exactly probably 28. Can anyone do this quickly?
Zero 0.35 for calcium.
So you get 0.35 and
0.5248.
0.5248.
Yes.
The other one would be also something similar.
Yes, 0.526.
0.526. You can divide everything by the smallest, so it's going to be 0.35, 0.35, and 0.35. What do we get? It's this is
1.49.
so approximately 1.5. This would also be approximately 1.5, right? So also remember,
Yes.
also remember, a lot of times the ratio is not going to be a whole number ratio. I mean, it's going to be close to a whole number ratio, but it would still be in decimals. So for example, 1 ratio, 1.5 ratio, 1.5. How do you convert that into a whole number ratio? You can either, you just need to multiply it by a number so that everything gets converted into a whole number, and that number in this case is going to be 2. This would become 2. This would become 3, and this would also become 3. So calcium is coming out to be 2. Aluminium would be 3, and silicon would be 3. So C is the answer. So remember, this thing, and I'm repeating that a whole number ratio is not always going to come. I mean, you're gonna get ratios like this. Like if you get 1.33 versus 1, let's say there are two substances. There's carbon and hydrogen. And let's hypothetically speaking, you get this ratio. You do everything and you get this ratio, 1.33 ratio 1. Now, to make it a whole number ratio, what do I multiply both values with? Or what would be the whole number ratio if you get 1.33 ratio 1? Like what number would I multiply this with? Especially this
3
one.
maybe.
Which one?
3.
So if I multiply both of them by 3, then 1.33 multiplied by 3 would probably be something very close to 4. So that's going to give you 4, and this would be 3. So 1.33 ratio 1 is 4 ratio 3. So always remember, think of a number that you're going to multiply something with, and to convert it into a whole number, because you're not going to get whole numbers every time. Similarly, let's say you got 1.167 and 2. I mean, this is the ratio that you're getting. What do I do? What do I multiply 1.167 with? I mean, that would be just trial and error then. Uh, I mean, this one is kind of very difficult, like to figure out what the ratio is in whole numbers. See, this one would be, I mean, 1.33 was easy, but you can
6.
6. Let's just
Yeah,
check.
that's using 7.
So 1.167, if I multiply it by, sorry. So this would involve some sort of trial and error. So what's happening? Just a second. 1.167 and multiplied by, if I multiply by 6, so I get something that's close to, that's almost 7. So that means I'm going to multiply both values by 6. So this would come out to be 7.00 something, and this would become 12. You got 6 into 2, that is 12. So it was actually 7 ratio 12, which was coming out to be 1.167 ratio 2. So beware of this. And I'll do just one more. Let's 1.667, and let's say 3. You got this ratio at the end. What is the whole number ratio? What do I multiply both values with? I mean, I don't care about this. You multiply this with anything, it's always a whole number. What do I multiply this with to get a whole number?
3.
You're going to multiply it by 3, because if you do that, so 1.667, you multiply it by 3 and you get 5. So multiply this by 3, multiply that by 3 as well. So this is basically 5 ratio 9. So just be prepared for this. In O levels, most of the questions in empirical formulas, you mostly got whole numbers. But over here, you might not get whole numbers. So just a few things about. I'm going to come to yield later. Just a few things about this one. Okay, there's just another. The thing about empirical formulas, I'm going to have to open a book. Let me quickly open. You're just trying to find another question. 1 second. Yes. Okay, let me just find some empirical formulas questions, some more. Can anyone spot empirical formulas? That's page 42. It's 32. So now this one, because I want to talk about molecular formulas. So yes, I want to talk about molecular formulas. Maybe there's a question on. I mean, there's empirical formula. Empirical formula, remember, is the simplest ratio. Okay, just trying to find a question on molecular formula. Uh, I said yes. This one. Let's try and do this question over here. Um, the molar mass is the molecular formula. It's the mass of the. It's the MR. Okay. So that's your MR, and let's try and do that. That's 150, and you're given 72%. I'm just going to copy this question, and we can try and do this question on the board here. So empirical formula gives you the simplest ratio. Remember, empirical formula gives you the simplest ratio. Now they've told us that the MR is 150. Now, for glucose, the actual formula is C6H12O6. But if you do the empirical formula thing, what you're going to get as your answer is going to be, it's going to come out to be like if you do the whole calculation and do the empirical formula stuff, you always get the simplest ratio. So how do you go from the empirical formula and you try and find the molecular formula? Uh, I mean, once assuming that you did all your calculations like the ones that we were doing right now, and you found the empirical formula, and now you want to find the molecular formula. For that, you need to know the MR. And the MR in this case is 118. So how do you find the formula? Assuming that you have the empirical formula and you have the MR, how do you figure out this formula? The way you do that is you find the MR of the empirical formula, which is going to be 30 in this case. Carbon is 1, so that's 12 plus 2, that's 14, and 16, that would be 30. So you figure out the difference, like how many times would it be 180? That's 6 times. So based on that, you can then figure out that the number of atoms in the actual formula, are going to be 6 times what is given in the empirical formula. So you multiply the empirical formula by 6. Okay, so to find the molecular formula, you need the MR. The empirical formula only gives you the simplest ratio. After doing all those calculations, you'll only reach here. You'll reach this point. You won't be able to find the molecular formula. And for that, you need the MR of the substance. So what you're going to do is you're going to compare the mass of the empirical formula with the molecular formula mass. And you'll figure out a factor. Okay, by what factor should I multiply the number of atoms that I have so that I get the molecular formula? So this question is going to be similar because the MR is already given. That's given as 150. And you're being asked to find out not the empirical formula, but you're being asked to find the molecular formula, not the you have to be very careful. Read the question properly. A lot of people would see this question and they would start finding the empirical formula. You just have to I mean, there's one extra step involved, and that would give you the molecular formula. So very quickly, let's somebody keep a calculator with you. Try and figure this out very quickly. It's carbon is 72%, so it's going to be 72% divided by 12. Hydrogen is 6.67%, and that's going to be divided by 1. And oxygen is 21.33%, and that's going to be divided by the AR of oxygen, which is 16. What are the values that we're getting? The middle one is 6.67. Baki bata do.
Carbon is 6.
So carbon is obviously 6. And what's 21.33 divided by 16?
1.33.
1.333.
So you get 1.33. So now again, what you could do is you can find divide by the smallest. So if you do that, divide everything by 1.33, do we get whole numbers or not?
Hydrogen is 5.
Okay, this comes out to be 5.
And carbon is 4.5.
So you're getting 4.5 again. So that means think of a number and multiply it by that number. What's that number? Well, everything should be multiplied by
2.
Okay, it's going to be 2. So this would become 9, this would become 10, and this would become 2. So the formula that we are getting is C9, and H is 10, and O is 1. Now that's the simplest ratio. Okay? That could very well be the molecular formula, but you have to uh, first figure out what the mass is. It's 9 carbons, so that's 12 into 9. Plus there are 10 hydrogens, plus there's 16. So what's 12 into 9? That's 108. Yeah, how much are we getting?
134.
Hey, sorry, oxygen is 2. I forgot oxygen is 2. Okay, so oxygen is 2, so there's another oxygen. So that's 150. So that means if the empirical formula and the MR are the same, so that means this is the molecular formula. Okay, you just have to multiply it by 1. That means the formula remains the same. If they had given us, if they had told us that the MR is 300, right? Then that would mean that the empirical formula mass is 150. So that means you would have to multiply all the atoms by 2 to get 300. And your molecular formula in that case would be C18 and H20, and the ratio would be the same, except the number of atoms would be twice the number of atoms that are shown in the empirical formula. Okay, is this clear to everyone? Mayim, is this clear? Zebi, Yasmin, is this clear?
Yes, sir.
So that's about empirical formulas. I'm not going to talk about. You can do the questions. The only thing is, be careful. Are they asking for the molecular formula, or are they asking for the empirical formula? Do this extra step. If they're asking for the molecular formula, you would need the MR of the formula, and then you can figure out the factor by which you would have to multiply the empirical formula to get the molecular formula. Anyways, the next thing we're going to talk about is about percentages. There's a thing called percentage yield. So what is percentage yield? Okay, so let's talk about percentage yield. Percentage yield is, the formula is simply it's simply actual, or you can say experimental, divided by the theoretical into 100. So that's your formula. So experimental is, now what's the theoretical? The theoretical, and remember, yield can be applied to anything. You get the same answer. You can input moles over there. You can input volume of a gas over there. You can input mass over there. Most of the time it's mass. TK, in a lot of questions it's mass that you're inputting there, but doesn't really matter. It's the yield would still be the same. TK, whether you, like, if you have a substance and you take the mass of the substance and you put that in the formula, you get the same yield. You put moles of that substance, you get the same yield. You put the volume of, if the substance is a gas, you put the volume of gas of that substance, you get the same yield. So it doesn't really matter what you put in there, but most of the time it's mass. Okay, so um, because yield has to do with output, and output is usually in mass. Okay, they're looking for mass of the substance. So anyways, what's theoretical? Theoretical is all that you have done so far. Okay, it's the calculations that you do on your calculator. So think of your calculations on paper. That's basically theoretical. Experimental is obviously what's actually going to happen. So for example, you have a reaction and there's sodium and it's going to react and it's going to produce NaCl and H2, right? And this is a balanced equation, and you're being asked what would 5 grams of sodium, what mass of H2 would be produced, right? So that's a question. Now, whatever you do on paper, whatever you do on your calculator, that's basically theoretical. You're not performing any reaction, so you can quickly find the moles of sodium, which would be
Sorry, sir, the equation is not balanced. Yeah.
exactly. One second. Everything. I mean, this everything would be 2. Now it's balanced. Okay. So you've got 5 grams. Now you've got 5 grams, and you can find the moles, which would be divided by 23, the AR of sodium. Okay, if you try and find the moles, it's going to be 5 divided by 23. So quickly doing 5 divided by 23, I get this huge number. So let's keep it up to 3 significant figures. So it's going to be 0.217 moles, right? 0.217 moles. And the moles of H2 are going to be half of that. So it's going to be the same moles. Divide them by 2 and I get 0.10, rounding off to 3 significant figures. That's going to be 9.109 moles. And I can find the mass. I just need to multiply it by the MR. So if I do that, I'll find the mass. So if I find the mass, so I'm going to multiply this by 2, which is the MR. It gives me 0.217 grams. So anyways, coming, not 271, 0.21. So I'm going to get 0.217 grams. Anyways, we did all this calculation. This is our result. That somebody asked me what mass of H2 gas is going to be produced, and it's 0.217. But I didn't do any reaction. This is just a hypothetical value. This is a value that I'm getting on my calculator. Reality might be very different. In reality, if I take 5 grams of sodium, a lot of things can go wrong. Firstly, how do I know that all of it reacts? Okay? Like even if you do a simple reaction, reactions don't usually go to completion. Like if you try burning a match, it's pretty hard to actually burn the complete match. I mean, you can try all you can. वो end में ना थोड़ा सा रह जाता है. It never really burns completely. So if you've got 5 grams of sodium, so and you do the reaction, then there would be some unreacted sodium. The reaction would not really go to completion. Then we're assuming that the 5 grams of sodium is very, very pure, which it usually isn't, because if you take 5 grams of sodium, there's going to be considerable impurities in it. In the real world, nothing is pure. So if you think of 10 grams of calcium carbonate or any substance, it's not really 10 grams of calcium carbonate. It has impurities in it. So the thing is that the values that you're taking are just hypothetical. Your assumptions are way out of, they're very different from reality. 5 grams of sodium in reality would probably be like 3 grams of sodium or 4 grams of sodium with 1 gram of impurities. 5 grams of sodium taking part in the reaction, probably just 70% of sodium would take part in the reaction, or 80% would take part in the reaction. Some of it would be unreacted or would get wasted, or there might be a small explosion and there might be a small piece of sodium that might fall off the container. So reactions don't happen fully, they don't happen completely. So the mass of H2 that you're going to obtain would be lesser than that. And yield is that what percentage, like, is it, what are you going to obtain? This is the maximum. This is known as the maximum yield. The theoretical value, okay, whenever you hear the term maximum yield, all the calculations that you do on your calculator, that's your maximum yield. That is what you're going to get if everything was pure and the reaction happened fully and nothing went wrong with it. So that's the maximum output that's possible. In the real world, you always get a value that's smaller than that. So it might be 0.1 grams. It might be, I mean, it could be really off. I mean, it could be very different from this value. So you want the yield to be really high. You want it to be closer to 100%. But even something that's close to 70 or 80%. In a lot of reactions, even a very, if you talk about fermentation of alcohols, that just has a yield of 5 or 6%. So a lot of reactions, the Haber process, it has a terrible yield. So a lot of reactions, they have really bad yields and you have to live with that. The reaction just doesn't really happen fully. But you want the, in the chemical industry, you want the yield to be really, really high. You want to use pure substances, you want maximum output. So first thing, whenever you hear the term maximum yield, uh, that's the theoretical one. That's the one that you get on your calculator. 70% means, if the yield is 70%, that means whatever you calculated, you're just going to get 70% of that in reality. Similarly, if you get a yield of 20%, that means whatever you have calculated, you're going to get, in reality, you're going to get 20% of that. So you just plug in these values and you find yield. So for example, theoretically, you've figured out that you're going to get 100 grams of hydrogen. You did the experiment and you got just 5 grams. So multiplied by 100, that means your yield is just 5%. That means you're going to get just 5% of what you estimated. Okay, so is this clear? Percentage yield, the formula. Okay, we're going to. Is this clear to everyone? Kausa, is this clear? Aisha, Aiza, Ahmed?
Yes.
Yes.
Achha, so we did empirical formulas. We're going to do percentage yield questions tomorrow, and then we're going to do another subtopic of moles. Okay. Try and do the questions in the worksheet and see if you have any problems. Okay. Chaliye, let's talk tomorrow then.
Okay, sir. Thank you.
Sir.
Okay, take care.
Thank you.
Allah Hafiz.